Hi everyone, welcome to week 5 in object-oriented programming. Today we will talk about polymorphism and exception handling. We started with the first of these topics last week, where we basically talked about inheritance and also virtual methods, virtual functions, where David and I presented you different ways to deal with inheritance and similar behavior that can be made virtual to overload or to inherit a function or a class in general. We will start with the first overview of where we are in the semester. So actually this week all about polymorphism and exceptions, and next week we will talk about operator overloading, and I think some topics that are still missing probably, or interesting topics.
Yeah.
Cool. As always, David will give us some short recap in form of a Slido.
Yes, I prepared again a short quiz for you, and I will give you time, don't worry. So I hope you can read it. It's a little bit small, but you should also be able to see it on your device. And the question here again is, what is the output? So we have a shark, or we have an animal class, like last week. We have a shark, which is derived from animal. We have a bee, which is derived from animal. And all these classes have a constructor and a destructor. And in the constructor, the letters here, the characters are lowercase in the destructor and uppercase in the constructor. And in the main, we create a shark, we create a bee, and then we delete the shark. And there is hawk. This is because I switched, but it shouldn't be a problem at all. It's just the variable name.
Today again with 50 participants, so what do you plan today?
I think we can wait for 50, yes.
Yeah.
So maybe we can start easily, hopefully easily. What do you think is the first character which is printed? What's the first one? What's your guess? A. Yeah. That's correct, because we're making a shark, and at first the animal part of the shark is created. Second one. S. Yes, because the shark, so the derived class constructor. Okay, maybe we go to the solution. The correct one is ASABSAA. And of course, we will have a look why this happens. So in the first line, we're creating a shark. So as we said, we're creating a shark. So the animal constructor is called, this is the first A. Then the constructor of the shark here, so the derived class is called, this is this S. Then we go to the second line where we create the B. And here again, the animal constructor is called, and the derived constructor of the B is called. So I think we agree all on that. But we have one problem here. So we delete the shark. So the destructor of the shark is called. And then the destructor of the animal is called. And then we save this here into an animal pointer. And then we delete the B. So first the animal part is, or the animal destructor is called, but because this is just an animal here, or it is stored in an animal pointer, and we do not declare here any virtual, only the animal part, so only the base class is destroyed, and the B destructor here is never called. So as I said, the B destructor is not called, and how could we solve it? We could solve this issue by making this animal destructor virtual. Any questions to this? So when we would write virtual destructor animal, then the program would recognize, okay, there might be a derived class, in this case the B, and then I would also call here at the end, or here in between, the B of the destructor of the derived class. All right, when there are no questions, maybe we continue with something which was left last time.
Right, yeah.
And I think we also, we kind of had a question last time how this would work. So with this setup we had before, it would be possible to create an animal. But we all know there are no animals which are just animals. They all have a specific type. So there's a lion, there's a bear, a fish, whatever. But there is no animal which is just an animal. And this is then called an abstract class, or also a pure virtual method, which can be used to create abstract classes. And what we do now is, when we say, okay, I do not want that it is possible to create an animal, so to create an instance of the class animal, and I can do this by setting at least one method inside the class to 0. And when I say it's equal to 0, then I will make it to an abstract class, and abstract classes, or I cannot create an instance of an abstract class. And what this also means is that all the derived classes, in this case the lion, have to override this function. So they have to implement this function, because otherwise it's not possible to create a lion. So this is here in the base class, it just says, okay, it should be possible for all the derived classes that there is a method eat, because I know that all of the animals can eat, but they do it all in a slightly different way. So in each of the derived class, I have to implement this eat method. I can implement it in each class a little bit different, but they all have to implement this class.
I have a question.
Yes.
For instance, if I want to have a method move, and move is in X, Y, and Z coordinate, which would be actually the same for everyone, I would say.
Yeah.
Is it also then pure virtual? So is it an abstract class then overall? Do I have to also say equals 0? Or how does this work? So when is the class abstract? As soon as I have just one pure virtual method, or do I need more of them?
So as soon as I have one method which is set to 0, it's an abstract class. And I cannot create an animal in this case. Right. Of course, I could have other methods here, let's say move, which is implemented because let's say all the animals move the same or in the same way. Even then, it's an abstract class and I cannot create an object of the animal because as soon as I have one method here which is set to 0, I cannot create an object of this class. All right, so maybe you know it from other programming languages because these abstract classes are also sometimes called interfaces. I think in Java they are called interfaces. And as I said, at least one method of the class is set to 0. Then we call it pure virtual. And then it's not possible to create an object. And as I said, all subclasses must implement all pure virtual methods from the base class. So if there are more of these methods which are set to 0, all of the subclasses have to implement all these methods. And it's often used to predefine behavior of subclasses. As I have said, eating, I know, or let's assume all animals eat, let's assume all animals move, but they do it differently, so we can create this abstract class, implement it, set it to 0, and then we force us in each subclass that we have to implement this.
Everything that we heard so far, so in the last week and also in this week regarding abstract classes, virtual functions, and these kind of things, relates to one concept of object-oriented programming called polymorphism. And this is actually what we use as a very handy feature to have the possibility to, apply the same method or like a similar behavior to different objects of different types. As we said, if we have, for example, a move that is different, for example, a species on land move in 2 coordinates and in the air in 3 coordinates, the basic idea is the same, the interface is the same because it's the move function, but the implementation is different. And this is called polymorphism, many forms, and that's actually the idea behind that. And this works perfectly nice as soon as I have a pointer involved or a reference involved. As we saw in also the last example that David had, as soon as we have the pointer, we have this runtime polymorphism compared to the compile time polymorphism that we talked about last week. And here I have to refresh it because I changed it just live because of the typo. These are actually the 2 types. We talked about that last week, compile time and runtime polymorphism. And the runtime polymorphism is the overloading of functions. And we will talk about the compile time polymorphism, actually, or this feature next week when we talk about operator overloading, which in my opinion is a really handy thing also in C++ and other programming languages, that we can define how an operator should be different for different classes, for example, for different objects, because we want to, add 2 objects and want to have a specific behavior. So we'll talk about this in next week's lecture. All right. What we also mentioned last week are virtual tables, actually. Just to recall a bit what we were talking about that particular concept last week's, we presented you that as soon as we have virtual methods, virtual tables are created. So virtual tables are a cool tool or cool implementation on the level of the compiler, where we actually can define how the polymorphism should look like. And here I have a nice example. For example, we have the base class and the derived class. And in these two, or in this example, I will now check how the virtual table actually looks like. And this will help us a bit to understand the V-tables and also virtual methods.
So you're creating a derived class and save it into a base class pointer.
Right.
And then call the methods speak, as a bSpeak and bSing. Okay.
Right. So we know what usually would happen.
Yeah. The speak is in a derived class also, so you override it.
Yeah.
And
sing is not implemented, so it's in the base class. I use the G++ compiler in that case with a specific compiler flag, and then run this example. And then we will see as an output here the probably a bit technical looking virtual table. And the interesting thing actually in this example is first here the speak method. Because in the virtual table for base, it's base and speak, which is kind of obvious because base is the base class. But, and now this is the interesting part, since we've implemented and actually we've overwritten the speak function, or the speak method, when we use the pointer, and we did this in the main, from the base class or from the derived class, here the V table says derived speak. So it calls the speak of the derived class. In comparison to here, where we don't have an implementation in the derived class, so we, in that case, just have a sing method in our base class. We don't implement it. And so in both virtual tables, we have sing from the base class. Under the hood, here another member is added, which is a pointer. We don't do this. This is actually something that the compiler does for us. So there is a pointer added pointing to the virtual tables for the base class and the derived class. And in this, when it comes to this situation actually, where it's calling the speak method, the compiler is checking, okay, what's in the virtual table, in the V table for speak, and then it goes like, okay, let's have a look. It's the pointer, it's like here, it's a pointer, and here it's a new derived, so it actually sees, okay, nice, in the derived class, take the derived speak, and in the other case, where we don't have an implementation for sing in our derived class, it also checks the V table for derived and says, okay, good, our plan or our fallback, we don't have an implementation in the derived class, let's switch back to the base class. This is actually how virtual tables are working.
So if we would remove the virtual here, what would be different then?
If we remove it here, we would also have the same situation as we have here, since we don't have a virtual here as well. So it would say base speak.
Okay, yeah. Can you say what this funny thing here means? Maybe.
This is also part that, so you can try it on your own if you're interested to do that actually. So if you just run it on your machine, you can generate it and you will get like a very huge file, because it does the same for IOStream if you include it and all the other libraries as well. So you have to really search for vtable or base or derived. Yeah, and what this does actually, this is a pointer to the function or to the methods, and this is something which we also talked about in ESB a bit, a function pointer actually, because the function is also segmented somewhere in the memory, and we actually say, okay, there is this function, and please go to this function and run it. Yeah, that's actually the idea behind the vtable, just to give you some context on that as well. Yeah, I think we had that.
All right. I think we now
Talked about ESP, yeah?
Yeah. We now move on to another problem, which might be, it could be that all of you faced that problem back in ESP, maybe. So we now move on from all these classes. We go to another thing called exceptions, but I want to do a short motivation about this. So let's suppose we have here a main function which calls a getConfig method and then checks if this getConfig returns a null pointer, and then, yeah, in this case, it returns 1 because maybe the config was not valid. And this getConfig method is then implemented, and this is called a read file, another method or another function, and we hand over a file name. And again, here we have to check the read file because it might be that there is an error when reading the file, and we have to return it again. And this read file gets a string, so in this case the file name, and it opens the file, and again we have to check if this file is open, and in this open file we opening the file, and here an error occurs because this file cannot be opened. I don't know why, maybe it doesn't exist. So what we have to do now is so here an error occurs, so this returns false. We have to return null pointer. So we have to check that this is a null pointer. We have to say if config is equal to null pointer, return null. And we have to check here again if this is a null pointer or null whatever. So this is a problem which often happens. I think many of you have seen also this problem, because every time you call or you have an error inside many subfunctions, you have to return it back to the main when you want to end the program there. Yes? I think that's just a typo. I mixed it up. I think there should be also a null pointer there. I would prefer null pointer instead of null. Null pointer is the C++ version of null, so I would recommend to use null pointer here. Okay, so basically what we are doing like this, so we're calling the main function, which calls the getConfig, which calls the read file, which calls the open file. Here we get an error. So we return the error to the read file, we return the error to the getConfig, we return to the main. This creates so much code for us where we always have to check the return values of each function call. And yeah, it makes program long and complicated code, and we have to handle the errors and propagate it again back to the next function. And luckily we have a solution now, because we will introduce you to exceptions. And I will just want to dive into it with an example. Let's change it a bit and say in this open file, we say throw null pointer. So throw is the keyword, and it says we throw an error here. So here is an error and I want to throw it. Then in this read file, in this getConfig, no action is needed, because this throw here, let's say it flies until it is catched by somebody, and I can catch it in the main function. So it is thrown back to all the functions which are called. So at first it is called here, it is thrown out of this read file, it is thrown outside of this getConfig, and then it comes here to this main function, and here I have a catch where I catch a char pointer. So a null pointer is a char pointer in this case. I could also use an int pointer, that doesn't matter. And then I can use this section here to react on what happened. Yes?
What if you have some memory in between which is not freed yet? Isn't there a memory allocation error then? Or?
Great question. We will come to that. But the cool thing is, in this section here, you can handle all this. So you have access maybe to the memory, and you can free the memory here, if that happens.
And if you don't deal with that in the main, and we stay in the throw terminology, you get that right into your head, because then the program will actually break down. And so at least there should be a point in your program where you deal about the exception.
Yeah.
Or care about it, yeah.
But we will also come to that. Okay, so generally, we will talk about it now, the remaining lecture, so don't worry if you haven't get it until now. Exceptions, or Ausnahmen in German, makes error handling much easier because they transfer the handling of the error to a desired section in the code, and you do not have to deal with this error handling in each function you're calling. And what's also very cool is it stops the current execution wherever an error is thrown, and then it continues somewhere else where the error is catched. So this is the general syntax. As you have seen, we have the throw keyword, and this throw should be inside of a so-called try block. So this try block, so everything what is inside of this try block is checked if an exception is thrown, including all subfunctions. You can have arbitrary subfunction inside. Everything what is inside of this try block will be checked if there is an exception. And then after that, you have these catch blocks here. And you can have many catch blocks. We will also come to that. And here in this catch block, you can do something. You can react on the error which you have received now. And then say, okay, depending on which type of error I get, I want to close the program or exit the program. I want to continue the program. Maybe the user input was just invalid and I want to ask the user again for input. So there are different kind of errors which can occur, and depending on the type of error, I can react in this catch block then, how I want to handle this. Okay, a short quiz from my side again. I know we haven't heard much about exceptions, but let's see what you say is the output for this example. Can you reach to 50 again?
I counted, we're about 80 people in the room, so it should be 50.
Have you already solved it?
Yeah.
Okay. Okay, 4 more. Yes. We are
Yeah,
at 50.
nice, great.
Great. Okay, let's see what you voted for. Yes, many of you voted correctly. Great. So the correct output is run exception, because obviously we came to this statement here in the beginning and we print out run. This works. Then we throw an exception here, in this case just a number. And as I said, as soon as an exception is thrown, the code stops executing at this point, so Hermione will never be executed. Executed. I have to work on my pronunciation, yeah.
A bit.
And so this line will never be executed, and it will be catched here, and we print out this exception here. All right, this is again the solution. So it stops immediately. We print the exception here, and I skipped this one.
You actually told us that we don't talk about classes and stuff anymore, but I think we should talk a bit more about classes, because C++ is object-oriented in a way that also when it comes to exceptions, we need to use our class knowledge that we have. And the cool thing is everything of that is working perfectly fine just because we have this hierarchy of inheritance. And what C++ does, C++ has a specific class, a base class called exception. It's in the standard library, and with this exception class, we also have some derived classes for specific cases that we have. Bad alloc, bad cast, bad type ID, bad exception, whatever. So we have a huge number of different exceptions. And the cool thing is that C++ uses this also. So it's not just we that care about the exception handling, it's also C++, or the compiler actually, that also has some exception handling already implemented. So for example, if we have a vector with 3 elements and we access the 5th position of a vector, we will get some troubles. In C, we had also some troubles, not checking the boundaries. We know that this had some annoying behavior when we were out of scope actually. But here in that case, C++ or the compiler will do this job for us and say, okay, 3 elements, you access the 5th element, it throws an exception, out of range exception. If we check this list, we see, all right, there is actually a out of range exception. And if we check further, we see that this has something to do with another class, which is the base class of the out of range class. It's the logic failure class. And again, because inheritance also is cool here, this also goes back to the mother class, to the base class of everything, the exceptions or exception class. Another example that we're having here is the invalid argument. With S to I, for example, could throw an invalid argument exception. So there are a couple of methods or functions in C++ that might throw some errors, and then we should catch these errors.
So in C, when we did something like this, I know we had a vector there, but when we indexed out of our boundary, we normally received a segmentation fault. And now, at least when this out of range error or exception is thrown, we can react on this. It's not that, as soon as we access it, the program stops and there's a segmentation fault, but we at least have the possibility to react on this exception. We can catch this exception, and then we can, react on that. And let's say if this number here is a user input, we can tell the user, you're wrong, please enter another number. So this is very cool, and it helps us a lot also with memory access, for example. Yes, this is
Speaking about
thing.
memory access,
Speaking about memory access, in assignment 1, we give you all the freedom that you did or do not have to check for memory. This has a reason, because we haven't learned about exceptions that time, but we will learn it now. So if there is no more memory available, C++ code will throw a so-called bad alloc exception. And it's so when you have the new keyword, you don't have to check for a null pointer which is returned, because the new keyword will not return a null pointer. It will throw a bad alloc exception. So in this case, you must catch the bad alloc exception and most likely end the program, because there's no more memory left. And usually I would suggest that you will do it in the main function. So for example, we have a main function which calls a func function, and here we have an integer array created. We get a pointer back. Then we might do something here, doesn't matter in this case, but if this is not possible because there is no more memory available, here an exception is thrown, and you have to catch it here in the main function. So you say, okay, in this case, I don't want to catch, let's say, an integer, or I don't want to catch a pointer. I want to catch something which is of type bad alloc, so of this class bad alloc. Usually, you catch it by reference, because otherwise there's always the thing that is copied, and it's unnecessary that it's copied. So you catch this bad alloc exception, and you can give this exception also a name. Most of the time it's called E, because you do not want to write that much. And you could have here the possibility to free some memory. I think that was also a question before. So let's say we have already some memory allocated. Here in this case, you have the possibility to free other memory, which is currently allocated, and then you can return with your desired return value here. So from now on, in assignment 2 and assignment 3, please use that bad alloc. It's not that big deal anymore compared to C, in my opinion, because in C you always have to check if it's null, and then go all this way back to the main function and use the correct return value. In this case, it's much easier, because you just need this try block here, where you can call all your subfunctions, and if wherever is a bad alloc exception is thrown, you can catch it in the main function and then return with the return value. All right. Any questions to this?
Okay, then let's go to the next thing that I spoiled a bit.
You spoiled a bit,
yeah. Sorry. But we might have the case where we don't catch the exception. And I think this is a reasonable question to ask: what happens if I don't do that? So what will happen at the end? And we know that computers or compilers, they will care about these things. So, for example, if we have an exception here, so we have this main function, and here we have the vector, and we access a place in the vector which is not available, something will happen actually. It says terminate called after throwing an instance of out of range, which is the exception that is thrown. What? I don't know what this is, which is 10, this size, blah, 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 aborted. So, bottom line, the exception should be catched or caught somewhere. Otherwise, we will get some issues. We will, terminate our program.
So it's cool that you said blah, 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 because I think this is important what stands here. Because the compiler or the program tells you you are accessing the element 10, so at the index 10, and this is greater or equal that the size is, which is free. So, of course, this is a silly example, but let's say this is something you have calculated or a user input, and sometimes it's not that obvious to see what's the actual value we are accessing here, and then it might help you because maybe you think it's correct, but it says, okay, you're out of bounds because the value is bigger or equal to the size in this case. All right.
We have a Slido again.
We have a Slido again, yes. So what's the output here? We have a main function with a try block, which calls a function called do calculations, and we have a catch block which catches an invalid argument. This catch block has here a cout which prints an I, and the function creates a vector of strings with red and blue. Then it accesses here, it makes stoy, so string to integer, and then it prints something again.
$38. Come on, people, a bit more. 40.
Yeah, it's not that easy, my opinion.
Yeah.
You already solved it?
Yeah.
Okay. All right, we need 2 more people. One more.
49. Yeah. All right.
Great, okay.
Let's see.
So what's the result? It's a runtime error, yes. Great that you spotted it. And the problem is, in our do calculations function here, we access the vector, which has 2 elements, 0 and 1, and we access it at the index 2, which throws an out-of-range exception. And this out-of-range exception is never caught, because here, in this catch block, we only catch an invalid argument exception, which would also be thrown.
But we will never reach this point, because as soon as we have this exception, the do calculations will stop here
Yep.
and go back to the function that called this, has called this function, and this is actually the main one.
Exactly. Yeah.
So we won't need the ST on the C out on the high, the last line in calculations. This will not throw a compiler exception.
Which one?
This here.
Doesn't have to, because we might have written using stdc out above, probably. This was just a small...
Yeah. So in general, you can assume that this kind of
In our code
errors-
snippets, this is never the problem.
Yeah.
Different because in the catch block it's STDC out.
Yeah, I know. Yeah.
C out.
But we would never reach that point here.
Yeah.
Okay.
Okay.
Yeah.
So
That's-
we talked about the exceptional classes and the cool classes which are already provided by C++, the standard class of exceptions, but we can also create our own exceptions. That's pretty cool. But before that, we need two more keywords or one more keyword we need to introduce. The first thing is no except, and that's kind of similar to const. When you remember back to const assures us that we will not modify the object. So in this case, we have a getter here, and we're just returning the age of the pet. I know that the age is missing, but let's say this const just means I will not modify the object. And no except is quite similar. It tells the compiler that this method here will not throw an exception. This is all. So it's kind of like a promise that we can make, and it's not really necessary to write it because it works without this keyword, no except. But it's just for us programmers that we can be sure that, okay, when I use this method, there will never be an exception thrown inside.
So
and
if you-
all the sub-functions, of course.
And if you check the C++ reference online, for example, and check if this or what this method does, then you also read this no except. So this is very handy, because then you can check, okay, what is the consequence if I use this method? Can there be an exception, probably? And the C++ reference will tell you, okay, this is a method where probably no exception might be, or there might be an exception, and then you have to actually take care about that as well.
All right. Another thing what we need before we can create our own exception is we have a short look into the exception class, this base class std exception, and it has, and now it gets complicated, a virtual const char pointer const no except function, which is called what. And this is basically just a function where you can define your error message. And this is, a method in the base class, and you can override it in your own class to create a custom error message. We will come to that now, because this is our own OOP1 exception we are creating, and we derive it from the base class std exception.
And this is the crucial part, actually. We have to derive everything that should be an exception from the std exception, as we already have seen that other classes or other exceptions do the same.
Yeah, we have a private member message, which makes sense because we want to have like an error message. We need a constructor which takes a message, and we set this message to message. And then we override this what function, and we return this string as a C string, because this what needs a char pointer as return value. And when we create our own exception class like this, so we override the method, And then let's say we have a main function and a create array function, and we throw here our own OOP1 exception with the error message, we crashed our program. And in the main function, we have a try block, which calls this create array function, and then we catch our OOP1 exception per reference. And the cool thing is, what we now can do is, we have this variable e, which is our exception, and then we can call here e.what, and the output is we crashed our program. So whatever we define here inside where the exception is thrown, we can then use this string in wherever we want, but in this case in the catch block with the what function or with the what method. That's pretty cool because based on what kind of error happens here, maybe it is a wrong user input or maybe it is just a programming error, we can define different error messages when throwing the exception, and then we can just print whatever we defined before when we created this exception here. Yes?
What would happen if you declare the function as no except, but then you still throw an exception?
When you declare a function as no except and you throw an exception inside, the compiler will not allow it. So the compiler says, this is not possible. You cannot declare a function or a method or a function as no except when it throws an exception. Yes?
When do we use no except? Because it would be really ugly to write no except behind every getter and set down.
That's a good question. When do we use no except? So of course, it does not make sense for every getter maybe, but it would make sense for huge methods which are hard to understand in the beginning. So if you have a method having or calling 10 other methods, and it's about, I don't know, 50, 60 lines long, and then your colleague in your group have to read all through this and have to see if there is an exception. That's hard, unnecessary work. So in this case, if you're sure that there is no exception thrown inside, it would make sense there. Of course, if you have a one-liner, it does not make sense to write no exception or no except. Any other questions? All right. What you also can do is we can catch more than one exception. So let's suppose we have here again our function which does whatever we want, and this throws any kind of exception. So maybe we have our own OOP1 exception which is thrown there. It could also be that we have a bad alloc exception thrown because we allocate some memory inside. And it could also be that there are some other exceptions thrown inside. And in this case, we want to catch all the exceptions because we want to catch all exceptions which are from the base class exception, which are basically all exceptions, all exception classes, because all exception classes have this exception class as base class. So when there occurs any exception, it will go down, go to the first catch here and see if this matches. If it's not matching, then we go to the second one, second catch block and see if this matches and so on. If no one of this catch block matches, as we have seen before, then the program terminates because you didn't catch the exception. All right. I think the last Slido for today. Again, we have a main function with a try block and with 2 catch blocks, and we are throwing our own OOP1 exception, which is derived from the std exception class. And I want to know what's the output here. All right. Yes, we've reached 50 again. Great.
Yes.
So what's the solution here? Yes,
Wow.
general error is the solution. Great. Because it throws the OOP1 exception, and as I said, as soon as one of these catch blocks is the correct one, and in this case, this OOP1 exception is a derived class from the exception, so it is of type exception, because this is the base class. The general error message here is printed, and this one here is not printed, and this is also not printed. Great. That worked better than I thought.
Yeah.
Yeah. All right. So now we come to the highlight of today, right?
Yeah, I created an NFT.
So please show us.
So I think this speaks for itself. I tried to give you some nice visualization. Yeah, that's the first. So we have an exception there, and it goes back to the main and might cause some issues, yeah, if we don't catch it. And now we come to the part where it's caught. So we have an exception handling in the second function, and then we remove the bugs, yeah. You can buy it afterwards if you want.
Do you have this spray also to buy?
Yeah, sure, I have it in my office if you need it. All right, yeah, so keep in mind, catch your exceptions, and then everything will be good.
One more time.
One more time.
Yes. That's great. Okay, so in summary, it's great for us to have exception handling because we can now use error, or we can propagate the errors through many functions back to the function where we want to deal with that error. Usually the standard exceptions are thrown, or you can also implement your own exception. You could also throw, as we have seen in the beginning, just a number. You can write throw 5, but I would not recommend it because it's not that meaningful. I just want to have it as simple as possible in the beginning. I would recommend you to create your own exception classes, where then you can also use your custom messages, error messages. This concept of exceptions is used in many programming languages. C#, for example, Java, Python, and many more. Slightly different, but it works pretty much the same. and which is very important. And we want you to work with exceptions, but please only use it for errors. So errors in this case means that there is some problem in the program. You could use exceptions also for normal control flow. So for example, if you are in a subfunction and you want to end this function and jump somewhere else, you could do it with exceptions because you throw something, then you catch it something and you can continue there. But you should not do it. This is not good practice. And you will get point deductions if you do it like this. So please only use exceptions for error handling. For example, if user input is wrong, file is missing or file content is wrong, and so on. And another important thing, never throw exceptions in destructors. You can throw exceptions in constructors, but not in destructors because it might be that the object is not destroyed properly, and this will cause a memory leak then.
So last topic for today, won't take too long. Something that was mentioned already last week in the KU, where Mich and Jule talked about shallow copy and deep copy. Since, in theory, practical and lecture part is separated, we also wanted to mention this idea that every one of you who is just doing the lecture part also have heard about that. So we have a function or a class here called pet, and the pet class has two member variables, a name and a pointer with the age. I know this doesn't make that much sense, but I had to do an example that is short enough that you will get the basic idea behind that. Now we're having a couple of things within our public block. So here on the one hand, we have a constructor, takes a name and an age and also set that. And we also have here our copy constructor that we learned last week with a print function, and we have a setter for the age. What could be new or interesting here, we have new here, where we get some new memory for an integer on the heap as well. So actually, since we're saying here that we have a pointer to an integer, we have to to get that somewhere, and this is done here actually. So that's the basic idea behind this class. And here we have our main function, where we get the new pet, which is a dog, or the variable is called dog, Rex, 5 years old. And then we're making a copy of it. We're saying dog print. It should print the age of the dog and the name. And also here for the copied dog as well. And then we set the age for the dog. And now the question is, where is it actually changed? In both, in just one? And to make this a bit more obvious and clear, I have again, great visualization. Here we have our first dog, the dog object, and the age points to a very, very small space on the heap where I have just the number 5. And in that example, our dog copy also points to the exact same one. And this is called a shallow copy, because we just copy the variables from the stack actually here, and the heap memory isn't copied. So it's the same. The reference goes to the exactly same object on the heap. In some cases, we want to have that, but if I say I want to create the new object, I probably don't want that, because if I delete, for example, the original dog, then the dog copy also might lose the access to the heap space actually. And this is why I need something different. And so we create another copy of an object, but in that case, we have to have a look here at this code where I have a copy constructor. And since we talk about that we are copying something, we might want to think about the copy constructor in that example. And here I say, okay, in case that I want to copy something, I don't want to have exactly the same. I want to have a new spot on or a new place at the heap. And so I will do that here. So instead of this example where I just copied age, I said here, okay, I need some space on the heap. Please give me the space on the heap. And then this changes to this, where I have then two separate spaces. And that's a cool thing, because if I would change it in the shallow copy example, then I would change it for both dogs. And this is not what I actually want to do, because I want to use or to deal with the copy in a different way. So that's actually the idea behind deep copy and shallow copy. Here I try to write it down once again for you. So shallow copy copies everything from the original object, but the heap might cause us some problems because it doesn't allocate new memory on the heap. This is the reason why we have to implement a deep copy as well if we want to do that. So there might be some cases, especially when no heap is involved, where shallow copy is perfectly fine, but in the previous case, we will definitely want to reserve some extra space. Otherwise, we would have two dogs which are different, but would have the exactly same copied age. Yeah, I think
that was it from our side.
That's it for today. 4 minutes before time. That's good, actually. So thanks for being here. Next week, we will talk about overloading. Yeah. And yeah, see you then. Bye.
Bye.